Let's compute another potential function. In this particular case, we have a vector field with two coordinate functions. I mentioned this in the last video. So we have coordinate functions m and n. So in order to show that f is conservative, we just have one equation to verify. That is, the partial of m with respect to y is the partial of n with respect to x. That basically zeroes out the third coordinate when we have a vector field curl in three coordinate functions. So here's our vector field. The first coordinate m is 2xy e to the 2x squared y, and the second coordinate n is x squared e to the 2x squared y. So first, let's show that f is conservative. So we're going to take the y partial of m. So again, we'll use the product rule. So for the first factor here, we'll just get a 2x, and then we have e to the 2x squared y. And then we differentiate the second factor. So we have 2xy, e to the 2x squared y, and then we do the x partial of the power, which just gives us 2x squared. So now we just clean it up. The first term is the same, 2x e to the 2x squared y plus, and then moving the 2x squared around front, we get 4x cubed y e to the 2x squared y. Now we look for this particular partial. So we take the x partial of the second coordinate function, which is the n. So again, we have the first factor. That will give us a 2x times e to the 2x squared y, and then we take the derivative with respect to x of the second factor, so that gives us x squared e to the 2x squared y, and again differentiating with respect to x, we get a 4xy here. And so again, transposing to the front, we have the 2x e to the 2x squared y, and then another term just like this one, 4x cubed y e to the 2x squared y. So f by definition is conservative. So equivalently, if f is conservative, there is a potential function such that its gradient equals f. So again, we do the partial integration. So again, the x partial of the potential function will be our first coordinate of the vector field. So the x partial equals 2xy e to the 2x squared y. So now we can do partial integration. Now, this is just rigging like a Cal-1 integral, because when we look here and we take the x partial, we get a 4xy. We have a 2xy here, so we're going to have to multiply by 2 to get the 4xy, and then of course pay for that factor of 2 with a 1/2. And so now this is table ready. This is just e to the u du. So we get 1/2 e to the u, or e to the 2x squared y, plus an arbitrary constant, which can be a function of y. And now for the second partial integration, we'll have the y partial of the potential function is equal to n. That is equal to x squared e to the 2x squared y. Now we do partial integration with respect to y. So again, just like we had before, we look up here and we see the y partial will give us 2x squared. We have the x squared, so we need to add the 2 here to make this table ready, and then of course pay for it. So again, we have e to the u du. So our integral will be 1/2 e to the u, that is 1/2 e to the 2x squared y, plus an arbitrary constant, which can be a function of x. And now we just compare the equations for f and we're good to go. We see that we must have this term in the potential function, that is 1/2 e to the 2x squared y, and then of course we can add any arbitrary constant and we will have a potential function for the vector field f. And we are done.